The plan for today, talk about crash recovery in file systems. Robert, I think you touched on this is a challenge, and we're going to basically spend most of the lecture talking about this particular challenge. And the problem is the failures, power failures. There's a risk if you're not very carefully that power failures leave the file system in an ecosystem state. And so you do a set of, let's say you implement some system called Live3, it does a bunch of disk operations, and you fail or power fails halfway through this set of disk operations. And if you're not very careful, then the disk will, after that, instead of after half of the disk operation supply, be in an ecosystem internal state. And so we need to have a mechanism to solve that problem. And so there's two solutions that we're going to talk about. Number one is something that it doesn't really have an official name, but I'll call it synchronous write. Right. And that basically what you do, the idea is you're sort of very careful which writes you do synchronously to make sure that actually at any particular point in time the file system is in a good enough state that later on you can repair it. And this has been in file systems the traditional solution until pretty recently. ext2 actually, the Linux ext2 file system actually has sort of a synchronous write type solution. And the reason I want to talk a little bit about it is because it seems like actually a pretty reasonable thing to do, but it turns out it doesn't work that well. And so then the next design, which is basically the current, what most file systems implement today, is a logging design. And one reason to actually go through a little bit of the synchronous write solution is to actually start appreciating how elegant or how cool the logging design is. Because if you sort of see it, maybe you're like, oh, well, that's obvious. If you had given me this problem, I would have done immediately logging. And so hopefully you get a little bit more sense about what the, why logging is a good idea. So that's the plan. But before jumping into that, let's talk a little bit about the homework solution for today. So the homework solution, correct, was implementing big files. In XE6, the maximum file size is, whatever it was, 12, or 11 or 12, yeah, 12 direct blocks, correct, plus 128 indirect blocks. So we have to look at the structure of the, this is an inode, it has a bunch of direct pointers, 12 of them. There's one indirect pointer, correct, which is basically a number of this block that contains then pointers to other disk blocks. The block numbers are other disk blocks. Right? And since the block is 250, the sector is 256 bytes, divided by 4, I guess you have 128 of block numbers in the sector, and then this is number 13, that was the indirect block. Right? So in total, the maximum file size in XE6 is distributed view is 12 plus 128, 140 blocks, or 140 sectors. Which it's not good for anything, basically. You can store music, some amount, right? And so your goal, or your challenge for today, was to basically extend this design so that at least you can have larger files. And the main point of this design, of this exercise, was sort of for you to realize that basically what it's all about is sort of an exercise in terms of implementing data structures on a disk. And you can implement the principle in many different ways. Right? You can use B-trees, you can use any other type of data structure. But we were asking you to do something really trivial, just to get a sense about what actually, what the sort of simple solution is that you can do. And in fact, this simple solution is what our original Unix file systems actually used to do. They actually, in fact, many of them still have a double indirect block. And so the basic plan was, I think, to add, to take away one of the direct blocks, you make 11 of those guys. And use the last entry to actually point to the double indirect block. And so the double indirect block There's one more block that points to a bunch of indirect blocks, and 128 of them, correct? It needs 128, and it points to 128 blocks. Okay, so that was the design we had to implement. And how large a file can you now, if you support double indirect block, how big a file can you support? You don't have to give an exact number, you just tell me how you compute it.
128 squared.
Yes, it's going to be 128 times 128, correct? Plus the original 128 that we have, plus then 11 instead of 12. Right? So it's 128 squared plus 128 plus 11, and that comes out to some number. Maybe 15,000 something. Still very small, correct? YouTube videos or long-term big YouTube videos wouldn't fit on it. But, it's better than the previous. And clearly, if you wanted to extend this, you could go to triple, in blocks, or you could just figure out like a totally different data structure that you may want to use. All right, so implementing it. I presume this is. Was this one of the easier exercises? Actually, curiosity. Yeah, or it should be one of the easier ones. So you only have to change one function, bmap. And so this is the original bmap function, right? And here's so basically the code you get to implement is very, very similar to this fragment of code, right? What deals with the indirect blocks. And in some sense, the only thing you have to do is basically replicate the code with one additional layer, namely the double indirect blocks. And so if my solution, which is not particularly elegant, but gets the job done, basically there's the check to make sure that you're at least addressing a block number that's within the maximum file size, so you have to have that check. And then basically it goes just through and sees if there's a double indirect block. If there's no double indirect block, it actually allocates this double indirect block, right? So this guy. And then you go off and basically you do the same thing again, right? Then you have to do the indirect blocks, which is similar, very similar to the code we just saw. And then finally you have to allocate the block. So instead of doing F and buff, with one BAlloc, you're going to get BAlloc for the double indirect block, the BAlloc for the indirect block, and then the BAlloc for the actual block. Right? And so for the rest, it's actually reasonable, straightforward. Right? And the only other thing you have to pay attention to is what you do with BN. Right? So to compute the whatever n for I index of the double indirect block, you have to divide by 128, correct? And to compute the whatever j index of the indirect block, you have to do mod 128. That make sense? Any questions about this? So you should have a good enough feel once you did this. Yeah, oh, sorry.
So just out of curiosity, you removed the lock on the buffer, like the buffer busy before doing the next part, which is also associated. But are there any situations where you would want to not do that and have them both maintained and then release them both at the same time?
I think in this particular piece of code, it'd be fine to maintain them both. There's no really harm. I think I've followed the x86 and generally follows the convention of releasing as soon as you're done. And the reason you want to do that, correct, is I don't know, how big is our buffer cache in x86? Anybody sort of paid attention to that? It's tiny, we set it to basically the smallest constants, possible, 10 or something, if I remember correct, right? And so in that scenario in the world, you want to not tie up the buffer cache with any blocks that you don't really need anymore. But yeah, no particular reason. But that's the main reason to do it, is to really soon so that you have space in buffer cache to throw, if you want to throw it out. Good question. All right. So clearly, hopefully you should get a feel that you could have chosen any other data structure, right? You could take whatever 006, pick your favorite data structure and use it to implement an on-disk data structure, right? All the data structures you've seen in 006 are in memory, mostly in memory data structures, but here is just basically the same ideas apply to on-disk data structures. Okay, good. All right, so let's return to sort of this crash recovery problem. And the real, just to sort of make an example of what the problem is, right? You might be in the middle of this code, right? And how many B writes does this code do? or log writes, it actually does quite a number of log writes, right? And so if there was no log, it might be the case, and you had a power failure, you could have failed at between any two instances of that, any instance of these disk writes. And so let's think a little bit about it. In this particular piece of code, right, let's say it allocates a double indirect block. Is it bad actually if there's a disk failure or power failure between one of these log writes? Like, what problem might you be worried about? Think about this data structure. So clearly during recovery, let's say we had a power failure. Clearly during recovery, it would be very nice if this data structure exactly looks like this picture. The worry is that during power failure, we might get in a state where actually this picture is not correct. And so how could that happen? Yeah.
So if we allocate a direct block and then we have a power failure, it would be empty, not have any
pointers, or block numbers to something else. Yeah. So yeah, exactly. So this is the kind of thing you have to think about, right? So for example, so let's take your example. There's one data structure is missing here, right? On this picture, that's pretty relevant, which is like the list of block, the free bitmap. Right? There's a set of blocks that's lying on disk that contains, the free bunch of blocks, and that basically is the free map. And what BL does, runs around in this free bitmap, finds a free block, right? And that's what's going to use to actually, create, say, the double indirect block or the indirect block. In some sense, what we need to arrange, correct, is that these two disk writes are atomic, because we don't want to end up in a situation where the worst situations could be that we have not allocated it yet, or not marked as allocated, but we're using it. Right? But what will happen if we come back in the file system? Well, this thing's great, the block is there in place, but at some point later, we might allocate it again, right? And then the same block might end up in two different files. Which, from the security point of view, would be a disaster, but, in general, presumably, it's not very happy for applications, right? We also could have the other problem, correct, that, the other option is to say, well, we'll mark it as free immediately, but then if we have a failure right after that, we might actually not use it in any of our file system data structures, and basically we're losing this blocks, correct? Is that clear? And so there's a set of invariants, right, that have to, on this data structure, as well as the free map, that have to hold across failures, or at least need to be repaired. And so that's the problem that we're sort of dealing with, is making sure that the file system or the on-disk data structures always stay in some consistent state that respects all the variants that have to be true. And so one block, for example, should show up only in one file. Right? And that's an invariant that needs to be true, and so we need to arrange that that's true. So let's look at a couple cases. So we see one case there on the board, but there are a couple other examples that I want to look at to see, just get a better sense about like how important it is to keep these invariants. So for example, let's say we look at creating. I'm going to extract a little bit away. I don't want to sort of show all the things that are going on, but basically two crucial operations in creating. We have two crucial writes. One is we're creating a new directory entry, which is basically writing the data block of the directory, sort of saying, well, X, so inode number, right, whatever, 10. We're creating X, and so we're writing, say, like, we can create X, that will, if X gets inode 10, then that would mean we write that information. And in addition, what we need to do is, actually get the new file inode, which may be 10. We might have allocated it first, and then do the writes in this order. Right? Now the question is, what happens if we have failure here? Right in the middle. Would that be good? Why not? this is the only disk write we've done, to actually create this directory entry. We have done no other disk writes. What could go wrong? Well, if we crash here at this particular point in time, have we marked on the disk that inode 10 is allocated? No, not yet, correct? There's no other disk write I've done. So basically, we could again have these sort of inconsistency between our free inode status and the inode section we are using, right? Because in this case, we would have a disk that X is pointing to inode 10, but in our free inode map, 10 is still free, so the system will come up at some point and decide, okay, well, inode 10 is free, I can still use it, right? So that might suggest, well, what you should do is like do the writes in a different order. Right? That would be one potential solution. You could say, well, what I'll do this write first, and then I'll do this write. So 1 and 2 in this order. And let's say the failure still happens in the middle. Right? So with the first one, so we mark the inode is allocated, but we don't actually create the directory entry. How bad is that? Yeah.
It's not as bad, but we still get an orphan to inode that will never get replaced. So.
Yeah, not particularly bad. Nothing really bad happens in the sense that when we're pointing maybe to an inode that somebody else is also using, but we might lose inode 10. Right? Because nobody realizes that actually it's not being used. Right? So that's create. So let's look at a couple more examples, and we'll see that sort of this recurring pattern of inconsistencies between on disk and what actually we intended to be true. And in some cases, like in the previous ordering, things are actually reasonable bad, or in fact, very bad. So again, let's take write, which is a sort of lesson we already know about. So let's say we write a block of a flag. Well, there's a bunch of writes involved, so we can do it first. Write block, the new block that we're writing. 2, we'll write the inode, but we have to update the inode, record that this file has a new block. 3, we maybe this is part of an indirect block, as we saw before, so maybe we'll write the indirect block 2. And we presumably have to update the free method too. And clearly we're going to have the same set of problems as we talked about before, right? Because we have 2 cases. Let's say we have failure right here. We're writing a block on the disk, but actually nobody has marked it yet. So there's actually, okay, nothing really that bad actually happens, right? But if the here happens, the failure happens here, this would be bad, right? Because we're writing in the inode that we're writing is recording that we have allocated this block. But on disk, in fact, we have not recorded that we allocated this block yet. And so we're going to have an inode pointing to a block that is maybe going to be later, that same block is going to be allocated for another file. Right? And the same block ends up in 2 different files. If this were the password file, we might not be so happy. Right? So there's all kinds of problems. You can all kinds of imagine all kinds of scenarios that go wrong. But the basic invariant that we're violating here is that every block should be allocated to at least at most 1 file. So this is not so good. Of course, we can switch the ordering around, and maybe our problem might be not so bad. For example, we might lose a block because we think it's allocated, but it's actually never used in any of the file system data structures. So the same problem that happened here and that we saw here, shows up in another form in this case. And let me use one more just hit this whole home. So let's say we do an unlink file. What we need to do is we need to free the blocks, right, that belong to that block file. And that means updating the free block map. We need to free the inode. Which means updating the free inode blocks. And in the inode blocks, there's a section of the disk that contains the inodes. Every block has multiple inodes in it, and then one of the bits, one of the flags in the inode is where it's allocated or not allocated. So free the inode, and of course we need to erase the directory entry. So now let's say that we fail here. So we get 2 of them right in, but not the last one. Our failure just hit at the wrong point. Ow, is that bad? Yeah.
Yeah, and then get a directory pointing to the file.
Yeah, you get a directory pointing to a file, well, to an inode, right, that has been freed. Right? And so what the risk is that that inode that has been freed will be used for another file later. And correct, now we have 2 files or 2 directory entries that point to that use the same inode, while we're not intending that to be the case. Right? In fact, the person that has this directory entry still pointing, the person that, the old directory that has this pointer still to that file, now suddenly can read a file that maybe it was never supposed to be able to read, right? Yeah.
At what point here do we decrease the reference counter to the inode? Is that in the free inode or erase directly?
This is like I could decrease the reference count, right? So let's assume that this has been. Yeah, the reference counts also would be inconsistent, right? Because we're going to have 2 directory entries. If the inode gets reallocated, we'll have one. This directory entry will point to an inode that has a ref count of 0, and then the other guy will point to an inode that has a ref count of 1. But like when we read, we never check ref count, so you probably would be able to read the file even though it's not your file. Make sense? So clear what the risks are. So this is not just a question of a small performance problem, or like this is basically serious bugs, right? Like to the point that the security, basically big gaping security holes. So we want to fix this problem. So this needs to be repaired. Okay, so what can we hope for? Like how good can we do, in terms of trying to avoid these problems? The most obvious solution is to do like one disk up write, and immediately do some synchronous write. Let me actually hold on for a second. Let me first walk through what our goals are. So what might be some reasonable goals? We need to, one, we want to maintain these invariants. So these are the invariants of like one block. Block is only shows up in one file, not in 2 files, et cetera, et cetera. On this data structure is consistent with the free map, both of the inodes and the free map of the blocks. One goal we might have, which is actually an unreasonable one, is that every update that we do to the file is immediately reflected on disk. So meaning that, like, if you write one block of the file, then all the bits that actually you wrote are at the end of the write system call are actually on disk. And that turns out to be, you could do that, but what would your performance be? Low. Yeah, so it is this like this, correct? So Robert, I think, talked quite a bit about disk performance, correct? And so 1 seek, correct, is 10 milliseconds. And so if you were writing after every block, you do a write system call, you wait until the write block has happened, so you're 10 milliseconds further, correct? In most files, if you do that for every block, and like creating a file, creates like 5 to 10 disk operations, correct? And so every one of them would be synchronous. That'll be 10 synchronous writes, of 10 milliseconds, which basically you will get not many file created in a second, correct? And so performance would be terrible. You would notice this as a big example. Like if you untar a big tar file, you would notice it, right? It will wait forever to actually get done. So generally, people are willing to settle for a weaker condition, which is all but the last, all but a few operations are reflected on this. fact, maybe most Unixes actually don't really promise you anything. When you do write, when you open a file, you write 1,000 blocks, and then you close the file. Unix possibly doesn't say anything about what you could expect. And certainly, you cannot expect that all the 1,000 blocks are actually on the disk. Right? And in fact, Unix typically has a separate system call. If you really cared about whether things are on the disk, there's a separate system called fsync that you're supposed to call to let the file system know that you really care that this data is actually on the disk. But you have to do it explicitly. And of course, only applications that really care, will do it. Most applications won't. Right? Yeah.
Is fsync guaranteed to push it to disk?
Fsync is supposed to guarantee. Of course, you have to look at the implementation of fsync and the file system that implements to see if it actually does. And in fact, there are all kinds of. Generally, yes, it does. But there are corner cases. Often the file systems get wrong. But yes. You look at the fsync manual, it says, I will sync the data belonging to that particular file to the thread, or to disk. Okay. But so this is already interesting. Right? You have to realize that this is true, and for basically performance reasons. Now, we do want to maintain the order operations. So if I created a file first and then created another file later, it would be good for the file system to guarantee that on disk it is the case that if file 2 exists on disk, definitely file 1 also exists on disk. Because there might be a dependency between the two. Right? There might be some script that the shell wrote that created file 1 first, then created file 2, and you're actually counting on the fact that that order actually is maintained. So we don't want to do file creation or writes really out of order because that may run the risk that some applications will break. All right, that makes sense? So these are the set of goals that we want to achieve. Clearly, we don't do something special when we're getting all kinds of trouble in these examples that I've just shown. Now, when we talk about fault tolerance, you sort of have to say what your failure model is. If you remember this from 6.033, correct, all the fault tolerance lectures started out saying, here's the failure model that we're assuming, and within that failure model, our solution is correct. So we have to do the same thing here. We're going to assume a very simple failure model, where the failure model, the only failure that we're going to allow is basically the disk, there's a power failure, and that's fail stop, meaning no more writes happen after that, no partial writes happen after that, just the disk fails. And we're not going to think about decaying disk blocks or any other random array, random bit changes or whatever on the disk block. Right? So it's a very simple model. You write to the disk, it happens or it doesn't happen, and that's it. Now, that's not completely realistic, but it's really pretty realistic. It's the first major concern you have to deal with. Right? How do you deal with decaying file blocks? How would you? This was an exercise. Well, we're not going to talk about yet.
But like in error correction code.
Yeah, checksum error correction code that either you can detect it and then report it, or actually fix it. Like in the best case, and many disk drives actually have internally built-in error correction codes. So it's not unreasonable to sort of ignore it for now. Okay, then another thing that we also have to talk a little bit about is like, why is this hard? Right? And the reason it's hard is really there's sort of this conflict between performance on one hand, versus safety. And we already see that in this goal 2, right? In some sense, we already immediately given up on actually achieving complete safety because we want to get decent performance. And so that in the rest of the discussion that we're going to have, this conflict is going to keep up, keep showing up. Now, I don't know how much Robert talked about solid-state disks. Clearly, magnetic disks are slow, with the 10 millisecond seek time. Solid-state disks are much, much, much faster. And so you might wonder, well, maybe we don't really have to worry about this anymore. We can just do as many writes as we like, and we can make them all synchronous. And that turns out not to be really that true. It's still true that sort of random solid-state disk writes are quite a bit more expensive, for example, than writing a whole bunch of blocks to the solid-state disk. So even though the damage is not as bad as on a magnetic disk, in fact, way less, it's still the case that there is actually a performance difference. And so we want to be careful with writing to disk period, whether it's a solid-state disk or a magnetic disk. And we like to use a lecture course to magnetic disk because then the differences are much more dramatic. It's like, oh, but that's so bad. You definitely don't want to do it. But in practice, there's not that much. People worry still about the same issues, even if you have solid-state disks. Okay. So let's talk about one potential solution, which is the synchronous write solution. Now, if you think about it, if you look at all of these different example problems that we saw with this, unlink, writing a file, or creating a file, they all boil down to one problem. And the one problem is you have some disk block like an inode or an indirect block or double indirect block that points to another block. And the risk that we continuously run, with examples, is that there's a dangling reference on disk. Right? Namely, this, for example, the reference might exist, but actually the target might not have been written yet. And then you have the danger that this target, this reference is pointing to some other block that actually you're not intended to be pointing to. Right? Because these pointers are always block numbers. And so there will be some valid block number in there, but it might not be the block number that, that block number that you're pointing to might not actually have the content that you're thinking it had. Right? And so this is, in fact, this is exactly what shows up in all these cases where, for example, here, if you write the directory entry, directory will create the reference, namely the reference to some new file, but the file itself doesn't exist yet because you hadn't written it yet, right? And so these all these problems that showed up are exactly an instance of this one problem here. And the way we looked at them is that if the reference exists, but the target doesn't exist, that's bad, right? Because that really means that the reference might be pointing to a previous file, or it might be reallocated, and you will have a reference to it now too. It's less bad if the target exists, but not the reference. Because at least the only risk of that is that basically you lose this inode or this block. But at least you're not pointing to something invalid. Okay? And so basically, all the problems I talked about is really trying to solve this dangling reference. So if you think about that, then there's a very simple protocol that you should follow for in the implementation of your file system. You should first always write the target, and then you should create the reference to the target. Right? So if you do this in a simple way, you would say, okay, well, step one is write target. But we have to be a little bit careful. If we start at the write, we really have to wait until that write completed before we create the reference. Right? So step two has to be wait for write complete. And then step three, once actually the target is on disk, right? That's perfectly fine for us to create the reference. And so step three is create the reference. If we think about this for a second again with our example, make it a little bit more concrete, we're creating a directory entry. We really want to assess is we have to create the file first before we create the entry in the directory that points to the file. Okay. Make sense? Yeah. Good.
So if a write target hits disk and the reference is also stored in disk, doesn't the file system actually guarantee that if the second one is visible, the first one is also visible?
So this, what's the first and second one?
So write target is the first one, create reference is the second one, right?
Yeah.
Since the reference is stored in disk, right, it will go through the file system, And the write target is also this, so it also goes through the file system. The file system guarantees.
But they may be in different disk blocks.
Yeah. So does the guarantee that order is observed apply to single disk blocks or over the entire file system?
Oh, only to a single disk block. But it doesn't really matter. The failure can happen after the first block is written and not the second block. The thing that we worry about is failure between this scenario. If we write it in this order, this is a good order to write things on. Because let me back up again. If we did the order and we did this first and then this second, that would be bad, right? Because then we would create a reference, but we're pointing to something that actually has not been initialized yet. In fact, not being allocated yet, and so we might reuse it. So we definitely want to do it in this order.
Yeah, no, my question was, do we need an explicit wait step or not? Like, does the
yes.
file system guarantee that already as it is?
No. We cannot assume that that the block that can be written. If we issue two disk writes to the disk at the same time, which we generally should assume that we can do, then there's no guarantee in which order they go.
Okay.
And so we have to wait for this one to agree. We want it in fourth order.
Okay.
Yeah. There's some disk interface where you can describe some dependencies, for as a file system writer, you don't really want to rely on specific disk features. Right? So by doing it in this order, explicitly waiting for the target, if we solve a problem that we're always pointing to something that is valid. Right? Now, it still can happen if we can get a failure here, and we don't create the reference, but we still have allocated the block. And so we need an additional plan to repair that part. Right? So this is the synchronous write. This part is the synchronous write part to the solution. That's one synchronous writing here, but that's not completely sufficient, right? Because we're going to have, we can still have the scenario where the reference is not created, but the block has been allocated. And now we have a file system and data structure where everything is consistent internally, except there are some blocks that are not on the free list, even though they should be on the free list. And so there's a second part to this, which if we do, so step 1A is doing the synchronous write, but then on the recovery, we have to do something. And so at some point the power comes back, right? The machine will go back on, and what we're going to do first is before we turn it over to the user, the file system is going to run some recovery code, basically a bunch of code to repair whatever damage there is. And so the one damage that we have to repair, right, is there might be blocks on disk marked as allocated, but actually not showing up in our file system data structures. Right? Because otherwise it means to having the missing reference. That make sense? So how can we repair this? How can we find these blocks that are not decorated?
The references will be zero, so you can just iterate through all lines and correct zeros.
Yeah, okay, so let's say this reference is 0, but it doesn't tell us that this block has been allocated, so it can not show up in a file system data structure. Yeah, go ahead.
Do you start at root and just descend down the whole tree?
Yeah, you start at the top of the file system, then you walk down the whole file system, and you record which blocks, and then the end, you look at the blocks that actually you're able to reference, and all the blocks that are not in that set must be free. Right? And so then you can go over your free map and look for any blocks that were not in your file system data structures and actually repair them and basically mark them as free. And this is exactly what a typical program, the program that does this is called FSCK. File system checker. It's a little bit more than a file system checker. It's basically a file system repairer. And it just goes over and rubs over your whole disk and repairs everything. So that basically all your variants that we're looking for are back into shape. And that's the synchronous write solution. In fact, that's the solution that people use for decades as your sort of standard file system. Okay. So what problems does this solution have?
Really slow. Maybe?
Yeah, go ahead.
FSCK needs to actually be run.
Sorry? Yeah, FSCK needs to be run, so is that a problem?
Yeah, nobody will run it explicitly until they run out of disk space, and then it takes forever. Presumably you have something you
Oh, yeah, you it's part of the init process, correct? You have no choice. It just runs. Like boot up, you boots, and part of the boot up, you run FCK.
The boot takes minutes.
Yeah, I guess that's what you want to have.
One problem is like you cannot do it, like for some file system you cannot do it when you mount that hardware, so you have to like unmount it and do it. So you cannot access data during the time.
Okay, so there's a little bit of sort of operational point, but I think the key point, is the one is the performance issue. So let's say you have, a couple million inodes in your file system, and most likely that those inodes are not nicely allocated next to each other because the traversal of the file system doesn't say anything about how the inodes are laid out in disk. So, it's a safe assumption to assume that basically every inode requires one random seek. So if you have one random seek is 10 milliseconds, and just make the model very simple, correct? Then how many inodes do you need before it actually starts running into the minutes? Huh? Yeah, like so like let's say to 10 minutes. It doesn't take that many inodes to get to basically 10 minutes FCK time, right? And in fact, one of the key problems that people had is like your disk would fill, and then you waited basically a half hour, before, or you had a power fill, and then you had to wait a half hour for FCK to complete. For example, if you do it on a modern disk, I think Robert had numbers from a little while ago, like for 70 gig disk, it was basically a 10-minute wait. And I can remember, like when I was a student, ISD would say, "Oh, we had a power failure. We need to run FCK," and then would send out emails saying, "Go do something else for the next 45 minutes." Sure. And so this is so the recovery time is bad, very bad. How about regular operation? Well, it's going to be bad too, right? Because you're doing the synchronous, for every target that you create, you have to do synchronous write. So in all our examples, so in creating files, there's going to be one synchronous write, at least one. For writing a block, there's going to be synchronous write. For linking, there's going to be synchronous writes. And so if you do a lot of file system operations, things are going to be very, very expensive. For example, you're inventorying like the Linux directory tree, source tree, or something like that. That's going to run for a long, long time on a file system that uses synchronous writes. Right? Make sense? So let's first talk a little bit about like what you could do about this. So the standard trick, to get better performance is to exploit the fact that there's a lot of RAM in your machine. Right? So let's talk a little bit about that. So how to improve performance is to basically use a write-back cache. And basically, as we go down to RAM, you basically perform and apply all your changes in memory. And you don't really do anything, you don't write anything to disk. And so you update your internal directory data structure, your internal inode blocks, and all that kind of stuff, just in memory, but you don't update them on disk. Right? And if you remember from last lecture, actually XP6 has a internal directory representation for in memory and one for on disk. And basically, what you do is you only update the in memory ones, and that was perfectly fine, right? Because remember that one of our goals. Yeah, we're only promising that we don't promise that all the changes to a file are actually reflected on disk immediately anyway. So we're only promising that the last few operations are not being applied yet. We can totally basically apply them only in memory, and then at some point later, at a convenient time, we'll actually write stuff out to disk. And when we write out something to disk, then we have lots of disk blocks to write out. Right? In fact, we're going to write out like big, lots of blocks at the same time. And it turns out that disks are very, very good at writing many, many, many blocks. and Robert talked presumably about this, that the latency to seek is slow, but once you're seeked, you can actually stream to the disk at basically 50 megabyte or 100 megabyte per second. So we can range it. Basically, we write a lot of blocks that are sort of close to each other. Then actually the disk will do a really, really good job of actually writing that stuff out. So this model seems, if we were just update our internal data structures, and then basically only once in a while we write everything to disk, that actually is sort of a great performance model. It's not so great for sort of safety, but we're already given up basically a little bit on complete safety. And if you really want something on disk, you have to call this fsync system call anyway, so that you can still do this as a model. So if you care about your files being persistent on disk, you call fsync. If you don't care, then perfectly fine. Then the file system gets this opportunity to basically batch lots of disk blocks. Right? Make sense? And so this cuts out all the synchronous writes. Correct? You don't really have to do any synchronous writes anymore. We just apply them all in memory. Now we have a small little problem, right? That when we do a batch, we want to arrange, that they presumably maintain some order, because otherwise we're going to run into file system inconsistencies. This is before. In fact, most file systems, until very recently, have sort of this kind of, so all file systems, including now, have user write back cache. And so the basic idea there in most file systems is either you flush fsync, or what a lot of Unixes did, they just sync like every 30 seconds or something like that. So just every 30 seconds, you take all the blocks that are dirty and just write it to disk. And then hopefully, and if you didn't have many disk write blocks to read, presumably that didn't matter in performance anyway. If you had a lot to write, great, because you get a huge disk throughput. Right? So that's the standard solution. In fact, but that has a bit of a risk. So let's look at that risk. So let's say we have the following scenario where delete X, like the file X, will consist of a bunch of steps, update free map, free inode, then next step, so there's a user or a program that actually creates these. And the next command, so one program creates X, another user actually, or another program actually creates a Y. So what will Y do? Y will allocate an inode. And then it will initialize the inode. And finally, it will maybe point it to a block, and then maybe it creates Y in a directory. So we would think about the sequence operation correctly in the context of a write back cache. Then what might happen is we would perform all these operations on the in-memory data structures. Right? And so I think it looks cool from the user perspective. All these operations might just happen, the user actually continues, everything's fine. But we could also run in another scenario where we've done these operations, and then the machine, and we're about to start. So one scenario is, the user does all these operations, everything is perfectly fine, machine fails. None of this stuff is being written to disk. It's too bad, right? But we didn't guarantee safety anyway, so it's not so bad. Right? And the user cannot expect things are safe on the disk unless they explicitly call fsync or syncing of directories, and we didn't do that. So that's okay. The real problem is, of course, is that when we're running sync, we're about to flush all these changes that are in memory onto disk, because maybe we'll do that every 30 seconds. And now, there's a whole bunch of stuff sitting in memory that has to be flushed and written to disk. Right? And we don't really know in what order these operations are actually being written to disk. At least we haven't done anything specific. So one order, could be that this write succeeds, and maybe this write succeeds. So these two, one and then the last one. So whatever file system change on this data change correspond to these two updates succeed, but none of the others. And is that problematic? Could FSCK repair this for us?
Yeah, well, this is problematic because Y now exists, but the inode that it supposedly points to has not been allocated in the coordinate. So there's no repairing that.
Yeah, there's no repairing this. There's no way that FSCK could actually, that synchronous write that combined with SSDK was crucial to get correctness. Since we don't have synchronous writes anymore, and we can't guarantee in what order things are written, we sort of lost. So there's no way that FSCK can repair this for us. Does that make sense? So that's a bummer now, right? Because now we've lost. While we can get back into an ecosystem data on this data structures without actually having a solution to actually repair it. Ever see that? And so here's where logging comes in. Right? Clearly, what we want is that if we flush, these changes to disk, we do it in a good order, right? An order that will help us later on to recover. And that is where, basically the coolness of the interesting part of logging. Okay. And so let me talk about logging. So, logging is something that databases have done for decades, but it's sort of new, or relatively new to file systems, in the order of a decade, basically. Sometimes it's also called journaling. Both words are basically used interchangeable. And there's a bunch of goals that a logging will have. We're going to make it easy for us to solve the problem. So first, system calls are atomic with respect to failures. So when we do a create system call, and even though the create consists of like 5 maybe disk writes or 10 disk writes, we'll arrange, our goal is going to be that all those disk writes happen or none of them happen. Which basically amounts to that the file will be created completely or not at all. And this is good, right? Because then hopefully we also have to do less work doing recovery, because either the thing exists or doesn't exist. And we don't want to avoid that we have to write these. We don't really want to run FSCK. So we want fast recovery. But we also want the speed of write back. So those are our 3 goals. Now, it turns out that actually doing a really good logging system is complicated. So we're going to do it in these 2 stages. I'm going to today talk about XV6 logging system, which is about the stupidest logging system you can imagine, but still can be called a logging system. And then for next week, not on Monday we have quiz, right? Don't forget Monday we have quiz. Next Wednesday, we'll look at how real sort of today's good logging system works. So in particular, what we'll look at is how ext3, the Linux file system that most people use still, how it does logging. And you'll see that actually there's a lot of complications that XV6 doesn't deal with, but that real file system doesn't deal with. In fact, this is the crucial point where we're switching basically from XV6 lectures to papers. So you should actually celebrate today. This is the last XV6 lecture. There's no more XV6 after this. And so here our goal today is actually just look at a very simple logging system just to see, how we can achieve these properties and how to do it. And then at the end of the lecture, I'll point out a bunch of things that actually problems with the x86 logging system. But that gives you a really good sense of like what the real challenges are in terms of building a real logging system for a real file system. It's not as easy as you might think. So the basic plan, though, is simple, which is often the case, correct? When you get to the details, it's complicated. So the basic plan is as follows. The way you typically do logging is we have our, we're going to basically use this write back cache. In order, to update data structures, inside our RAM. At some point in time, we'll decide, when it's time to write things to disk. But what we're going to do is we're going to maintain in memory first a little log that records, in what order these operations were performed. So, for example, if we update block 10 first, we're going to write down, we're going to update and write block 10. And then we'll write down write 11. Now, when it comes time to sync, or like write things to disk, we're going to do that also in 2 phases. So here's our disk. We're going to split our disk into 2 pieces, basically the regular file system, and then a piece that we're going to maintain around called the log. And instead of updating, when we flush, instead of taking these blocks and updating the disk immediately, the file system disk immediately, what we're going to do, we're going to write into the log. So we're going to first make all the modifications in the log. So we're going to write here, we're going to write 10. So we're going to, the new version of 10 is going to end up here. The new version of 11 is going to end up here, etc. And then we've done once we've done, like when we have put all the right, the dirty blocks into the log, we're going to write down we're going to write down the reserve one piece, one block within the reserve as a commit record. We're going to record whether we actually finished writing it to finish. So we're going to, let's say we're successful, we flushed all our changes to the disk, so all the new versions of these blocks are actually there. Then we're going to write a commit record. And this is the simple version of the plan. And the commit record records the fact that actually all the dirty blocks that we ran are in the log. Once we've done that, once we record the commit record grid, we're going to start installing, as it's called, all these updated blocks into their home location. So, for example, now we're going to, let's say, this is the file system, this is block 10, this is block 11. Now, at the installation phase, we're going to take the blocks, the new blocks of these, new version of these blocks, and actually write them in their actual location, the file system location. So when they're in the log, they're actually not visible to anything, to any application, right? Because they're actually not, those updates happen to be applied to the on-disk file system data structure. Only after we commit it and then install them, we actually apply them to the disk. So why is this good? Because you might think this is really stupid. Because now basically I turn every disk write into 2 disk writes, right? One first into the log, and then from the log actually onto the actual destination, final destination. Right? But think about this for a little while. The reason this is good is that if we, let's say, we're flushing, right? We don't actually write all the way. We never. Everybody awake again? Thank you. Let's say there's a failure. A power failure, right after we wrote maybe 10 or 11, but before we wrote the commit record. What do we need to do in recovery? Yeah, actually, we don't really have to do anything, right? Because we didn't read the recovery commit record to be done. Actually, there's nothing to do because we don't want to apply these changes because we know that not all changes are actually in the log yet. Right? So we can just ignore them. What if there is a commit record? What should we do in recovery?
You should go through and make sure that everything actually has.
Yeah, we need to just apply these changes. So we need to just write 10 into 10, we write 11 into 11, etc. Until we're all done. Right? Once we're done with we've written them all in, we can change the commit record to whatever we don't care anymore. So what happens if we, during recovery, we fail again? So, the commit record is there, we wrote 10, we wrote 11, or we wrote 10, but not 11, we failed. What do we do then?
You do it again.
We do it again. Exactly. Right? We start from the beginning again. We don't really care because these operations are basically idempotent. Right? We can do it as many times as we like. And so we can just start again. We'll copy 10 again back on this location. It will be exactly the same 10 as before, but whatever, we don't know. And we just keep, basically any failure doesn't really matter. We keep doing this until we actually lucky enough that the power stays on long enough that we apply them all, correct, and we erase the commit record. Now, the typical scenario, of course, will be that we just apply them and then we erase the commit record. But in principle, the scheme tolerates even failures during recovery. Right? Yeah, a couple questions. Yeah, go ahead.
So you mentioned like this turns every write to 2 writes, which we wouldn't like. So is and like typically in your stock process today, are you allowed to like not use logging if you don't like if you're just doing like some text editor stuff and you don't really care for different stuff?
There are ways of configuring a file system, but the answer is, in principle, no. You should know. I think the right way to think about it, you're going to eat the 2 writes, but we're going to, we'll see next week, right? Like how you can actually make this reasonable efficient, and that's going to be the. Notice that this write is not so bad, right? Because these are big batch writes, right? And disks are good at doing a lot of writes. It's mostly those costly versus costly individual writes. So basically what we can do is just take the whole block and give it to the disk and please say, update all these blocks. And it doesn't matter, right, whether in what order the disk does them, because we know if it gets through to all of them, it's fine. Right? So it's perfectly fine for us to give a whole bunch of disk writes to the disk and say, please apply them. Yeah.
Yeah, I was just going to say, so we can put everything in the log entry for this guy once, and then once those all complete, then we have to wait for all those all complete, and then we do the right.
Yeah.
Clear the.
Yeah, so this is important. So how many synchronous writes are here in this scheme? 1, correct? And what is the one? It's the writing the commit record. If we have to, we can't proceed until we have written the commit record. So this one has to be synchronous write. Yeah.
I have 2 questions. So the first one is we have to make sure that we never flush stuff to the log that exceeds the log size, otherwise we've overwritten the record, right?
Yeah, so that's going to be actually a big deal. We'll find, of course, this is always for the definiteness in the details. It turns out fixed like log is going to cause all kinds of complications, which will, and even in x86, the most simple logging system, it will have complications. Yes.
And then the second question would be, if a failure happens as we're writing the log before the commit record is written, then we have these entries in the logs that are not followed by commit record, but we somehow have to invalidate them so that when we append the next batch of stuff, the commit record after that does not reflect the 2.
Yeah. So one way to think about this is that there's basically only one commit record. When we start writing, we're always right from the beginning. Okay. And if we make it through and we're right, the commit record is written, then we're good. If it's not written, then we start from the beginning again. We don't have to do it. This does what x86 does. Of course, that's not such a great plan for a real file system, but so next week when we're reading the ext2 or ext3 file logging system, it will do smarter things. Any other questions about this? So this is the basic plan. It turns out, of course, tons of details to be worked out. So let's look at some of these details. So one other detail, well, this is actually not really a detail. We need to figure out, we need to deal with concurrency. Actually, there will quite a problem show up. We would like to allow multiple system calls to be named flagged at the same time, correct? And we have multiple cores, and it would be great if you can execute 2 file system operations in different cores. The problem with that is that so as we are sort of writing this stuff into the in-memory log, right, to record things, we'll have 2 operations in flight. Then we'll add dirty stuff to this in-memory log, and at some point we're going to apply all that to the real log, right, or to the disk. Now, one of our goals was to apply all the changes of the system call atomically. And so that meaning that we apply all the changes or none of them. So at some point in time, we're going to, whatever, we're going to be running around, we've updated some internal structures, maybe the 32nd hit, and we want to flush stuff to disk. Well, what can we flush to disk? Are we allowed to flush stuff to disk that is from a non-completed system call? Certainly not, right? Because then that would mean that we would have partial writes, a partial system call on the disk, and we run basically into the same problems as before, where maybe create has updated like 1 or 2 of the disk blocks, but not all of them yet, and so we're going to have not the final result on disk. And so we need to deal with the problem of actually having multiple system calls in flight. And so there's many ways in which you can deal with this problem. And in fact, the paper that we read about next week has a much more interesting solution than actually x36 has. But x36 basically says, what I'm going to do is I'm only going to sync when all system calls are completed. So when there's no outstanding system call, then is when I'm going to write things to disk. And if anything comes in while I'm writing to disk, I'm just going to block that system call. I'm just not going to execute it. I'm just wait until the disk, the logging system has installed everything. Right, and that will guarantee that we're never writing incomplete or partial system calls or results of partial system calls to the disk. Does that make sense?
So the problem that we're trying to that this solves is if like you're in the middle of writing to disk and at the same time a system call is writing to your buffer.
Yeah, for example, you have a create system call, not a create system call. They're updating the in-memory data structures. Maybe you want to call fsync, and you're starting to think, okay, it's time to flush my dirty blocks to disk. And you can only flush the ones of the system calls that are completed, but not the ones that are not completed. So the simple way of doing what x36 is like, okay, well, I'll only flush when all system calls are completed, like when there's no system call in flight. That runs into the problem that you mentioned, which is pretty hard, which is like, what happens if the log doesn't fit? All these system calls must fit in the log, right? And so x36 basically has sort of a, we calculated out like how many blocks a system call maximum will write. Right? So for example, for a create system call, we know exactly how many blocks it will write. Right? And so we just calculate it out and just pick our log big enough to hold at least a few system calls of blocks. Right? And so if a system call comes in and there's no space in the log anymore, or there's potentially no space in the log anymore, we just block the system call and finish all the other system calls, write out the log, and then proceed to the next system call. Does that make sense? And x36 is very easy to do, right? Because every system call runs on its own thread, and so it's perfectly fine for that thread to call sleep or wake up, or sleep until something has happened. Make sense? Now that's going to give us some trouble, correct? Because what happens if we have a write system call, which writes 1,000,000 blocks? You couldn't do that in x36, but maybe with your big file implementation could at least 15,000 whatever blocks, right? So we're writing like 1,000 blocks. Now, do we have to pick a block as big as 1,000?
Write returns how many bytes it actually wrote, so it's the caller's responsibility to rewrite anything that hasn't been written yet.
Yeah, write really doesn't guarantee anything. So basically what we're doing is we're just giving up this goal of system calls are atomic. It's only true for certain system calls, not for all of them. So it's not true for write. And so basically, we'll see in a second, the way we're going to implement that is basically we break write into a number of smaller transactions or atomic operations. Okay? So with that, let's look at quickly some code and see actually how things work. So use file write, just because there's sort of an interesting system call, because it may potentially take many more blocks than we actually have reserved per system call. And so the first thing it does actually, it computes the maximum number of blocks that the system call could write. And the way it does it, it computes, normally it looks at the log size and subtracts a bunch of blocks that we need to write in every small write. And so then, once it's computed, let's say it can only write 10 blocks, even though it needs to write 1,000. What it will do in a loop, it basically writes 10 in each iteration of the loop, and at each of those 10 are part of a transaction. And so you will see in x86 a bunch of code that basically says the form begin op, which says begin transaction, and then end op, which is like the end of the transaction. And so the begin op will determine whether actually this thing can run or not. We will carefully wrote it in a way that it actually can, and then it will perform all these writes, those 10 blocks, as part of as a guaranteed sort of atomic system call or transaction. So you can think about the beginning op and end op as marking the beginning and ending of a transaction. And anything that's in between in a transaction will be all applied or not applied at all. Right? And so we can then look at write I and see what it does. In fact, we already looked at it, right? What it does, it's going to, let's just take one of these. It's going to update maybe the indirect block and then write to the indirect block. And so it actually calls log write. Now, log write actually doesn't update anything on the disk at all. And we're going to see that in a second. Let's look at the logging code. Log write. So log write actually, the only thing it does, it actually records, as I said here, basically in an in-memory log that actually this block is now dirty. And that should be written at some point in time. Right? And so there's just an internal data structure that just records the fact that this block should be written to the log. And it will also record which sector that block should be written to. So if you want to write to sector 10, it will record this is a write here to block 10. And the data itself sits in the buffer cache, correct? And since it's marked as be dirty, the buffer cache will only evict it. Would it be bad? Would it be bad if the buffer cache evicted is right? If we're in the middle of a transaction?
Yeah, it would never get put to this.
Or it will be put there. Something needs to happen, correct? There's an interesting interaction between caching and the transaction system. Blocks that are dirty in the buffer cache, but that are not as part of a transaction hasn't been completed yet, we definitely don't want to install them in their file system place. Just cannot do that, because then that change would be visible to the application that cannot be visible yet, because the transaction hasn't completed yet. And so we take care of this by marking as dirty, and this guarantees that the file system won't actually flush anything to disk. Only flush now things to disk when we're done with our transactions. Okay? So that also means that how big should our buffer cache be? Well, it has to be bigger than our log, right? Because every dirty block that needs to be written to the log needs to fit into the buffer cache. Okay? So it's a slight complication, but not a huge one. Okay, so let's look at the begin op. So here's begin op. Requires a log, because we got to make sure that only one person writes entries into the log at a time, correct, with one processor. If we are in committing, we're going to sleep. We're going to wait until the committing actually has finished. If our operation won't fit into the log, and won't fit means we have it's more than the 3 blocks that are. We're going to just conservatively assume that it will write 10 blocks. Better than write more than 10 blocks. And then check if there's actually 10 blocks of outstanding free space for all the outstanding system calls in the log. And if it is not, we're just going to sleep. We're going to wait until actually things are done. So if everything works out, if all those cases don't work out, then that means there's enough space in the log for us to complete our atomic transaction. Right? And so we're going to just go proceed and actually do our transaction, our 10 block writes. So what happens at the end? When we finish the transaction, we check if if we're committing, then something really terrible is, we have a bug in our code. If the number of outstanding transactions is 0 at this point, then we're great, right? We're safe. It's totally safe to actually commit all the things that are in memory log, right? We can start writing them to disk. So if we do commit, so with outstanding was 0, and we decide to commit, we'll call the commit function, which is going to basically do what I said earlier. It's going to first take the in-memory log, this in-memory log that's here in memory, and actually copy it into the disk, right? And actually create the write-ahead log. And so that's the first part. So it actually writes everything to the disk. Then it writes the head. This is basically the commit record. And once it's written, the commit record is safe to install all the blocks from the log into the final destination, correct? There's no, at that point you can do it, and then you can write the commit record anymore again saying like, we're done, right? Things are good. So let's look at write log. So write log is pretty straightforward, right? It's just going to go through the in-memory log one by one, finds out which block needs to be put in the log, and writes it into the log here on this. Okay. Now x36 is terrible in the sense that it actually writes every one of those blocks synchronously, because we only have a synchronous write basically in x36. But that doesn't really, you didn't really have to do that. Okay. Let's see what else is there. I guess we can look at the write ahead. It's not that exciting. It basically writes a commit record in a particular place, so that you know where you can find it. Okay, boom, 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 boom. So what operations do need to be put into a transaction in x36? Other than file write, any other operations need to be put into transaction? Another way of asking this question is like, would you expect in the source code of x36 to see begin op, end op in lots of places or in very few? This is question 2.
Probably because it's better. What does that have to do with what has to go in transaction?
Yeah, okay, so what has to go in transaction? Maybe that's a good way to start.
I thought that was the original point.
Yeah, well, I'm repeating it, I guess. Maybe going from your angle, but so what?
I mean, one thing is that like anything that just happens in memory doesn't really have to be in a transaction, because if power is lost, all memory will be gone anyway. So we really only care about things that are consistent.
Yeah, go to this. So okay, so another way of asking this question is like, who do we imagine that begin up, end up is stringed all over the file system or only in a few places? So clearly, yeah, for all things that are not persistent, we don't have to worry about it. We don't want to expect anything there, right? But for things that may have to persist, we presumably imagine that everything that actually might persist needs to be in a transaction, right? Because it's going to update all these data structures. And that we want to make absolutely sure that we won't violate any invariants. Does that make sense? So it's going to be create file, unlink, write, like every file system call, right, that does any modification will be put into a transaction. And in fact, there are not many other file system calls. There are not many system calls in x36 other than file system calls, right? I mean, in x36, the bulk of the code is actually the file system. And so we'll expect basically to see begin up everywhere. And in fact, you will see when we had a bug last time somebody a little while pointed this out to us, that we didn't put iputs into a transaction because iput in principle doesn't do anything. It just decrements the reference count. Except if the reference counts go to 0, then that inode is actually freed, right? And part of freed, we actually might do a ton of disk writes. Right? Like all the blocks that were part of that inode need to be free too. And so in fact, every iput in the x36 code has to be put around in a transaction. Does that make sense? So basically any invariant that, anything that writes to the disk basically goes into a transaction. Yeah, go ahead.
So why can't we initiate a transaction into reference count?
So inside of iput, we couldn't do that, but there's also cases where we don't have to do that. There's It's a small. Yeah, go ahead.
Do any of these file systems expose the transaction to user space?
No, not really. Most file systems don't. And in fact, this causes all kinds of problems for applications that are writing sort of transactional applications. In fact, there was a paper at OSDI a couple weeks ago where basically it turns out that no of the user level application really works correctly on most file systems. Because people, the file system, well, there's a discrepancy between what the file system providers think they provide and what the application provider they think. And on top of that, the application providers often use fsync incorrectly. And it's also the case that the file system implementers don't implement file syncs completely correctly. And so here's like a big mess. But if you're careful, the paper's slightly misleading, because if you're careful, you don't have any of these problems. If you use fsync correctly, then it's all fine. But apparently a lot of people out there don't know how to use fsync carefully. Okay, so before closing, so what's wrong with x86 logging? There's a very simple logging system, right? Like it's 80 or 100 lines of code. Why is there anything else to be said about logging? So can you think about things that are... Yeah, the performance is actually terrible. First of all, we do synchronous writes for every individual write, even though we don't have to do synchronous write. But the bigger problem is we do write every block twice. We don't really take advantage of batching, so we don't really take a big batch of writes and actually write into disk. We write blocks eagerly, right? We only allow one basically transaction outstanding, or one log of transaction outstanding, not multiple. When we do commit, we immediately install things. And there are all kinds of optimizations you could do that actually don't require that. We have this weird thing where you have to sort of calculate in advance how many blocks you might need in the log. And we have a sort of weird plan for doing concurrent transactions. In the concurrent transactions, basically, we don't really allow them except that if they're perfectly 100% overlapping. Okay, so there's many extra problems. In fact, there's one basically bug in XV6. If we do an unlink, can unlink cause a lot of writes to the disk? Yeah, right, because if you unlink a large file, then all the blocks of that file need to be freed. That means all the bitmap blocks, that correspond for every block need to be updated. And in fact, if you look carefully at XV6 code, we don't calculate that correctly. In fact, we don't calculate it at all, because it's a little bit hard to do that. And so actually sync or unlink actually doesn't really work that well I guess it's not crash safe. There's basically no failures, no crashes during sync or unlink, at least for very, very large files. Okay, so that's last thing on XV6, other than, of course, it will be on the quiz. Don't forget, Monday, so no lecture on Wednesday, so that you can get lab 4 done. And then next Monday, we have quiz, which basically covers almost everything of XV6 until through today's lecture. Right? And so the quiz will be focused completely on XV6, as well as some of the labs, the JAWS labs.
What is it?
Yeah.
Including today or not?
Including today. All right.